It is officially recording, lecture 30.
It's the 27th.
That's right, it is the 27th. Why didn't no one yell at me the first time? You guys are at least you're paying attention. The funny thing is I should have just read my computer because it's right in front of me, right? We have chaos upstairs. Okay, so what did we do last class? So yesterday, we discussed, I guess I should learn how to spell. What did we discuss? We discussed that the key to understanding approximation is to start with what we call sequences in series. So these were two things that we introduced yesterday, a sequence and a series, and we gave you some examples of, excuse me, I keep like sniffling, I feel like that's rude, but it is what it is. We gave you some examples of sequences, and then we sort of left you with the idea that the important thing is that we study how a sequence sort of patterns. How does it behave? So in order to do that, we need some to be more specific. So let's sort of begin this way. So we ended class with the idea of studying patterns and limits. And we'll put patterns in quotations and we'll put limits in quotations. We sort of alluded to that this will be important. Okay, so let's see why. So to see why, we start with a real definition for a sequence. Yesterday we gave you the baby definition. We said it's a list of numbers that can be generated some way. That is true, but that's not a mathematical definition. So what is the actual definition? So that's what we need to write down now. So what is a sequence? A sequence is a function from the natural numbers or, if you want, we could say non-negative integers. That just means integers including 0, but not the negative ones. And they are a function that takes a natural number and maps it to a real number. So that is the actual definition of a sequence. So what we mean by that is, and what's going to prove to be useful is the following way of thinking about a sequence. Before I do that, before I switch this page, does anybody have a question? All right, so so what this means is, this means we can interpret the nth term, a sub n, as the output of some function. So a way of thinking about that is if we plug in n to that function, it spits out a sub n. And this is sort of what we did yesterday. We just didn't say that. So for example, if we had the function we had yesterday, the sequence, I mean, a sub n equals 1 over 2 sub n, then the function that we're using is this function 1 over 2 to the power x. So what we're thinking about is we're thinking about sequences are really just functions. The only difference is we don't care about all the outputs. We only care about the outputs when the input is a natural number. So you need to remember, what are the natural numbers? Those are things like 1, 2, 3, 4, 5, so on and so forth. And sometimes it's going to be useful if we use the 0 as a starting point instead of 1. So you could even think about it this way. You can even be more verbal. You can say if a sub n is this, then f of x equals this is the corresponding function. Now, this is extremely useful because you guys back in Calculus 2 studied limits. And that means everything we know about limits of functions should carry over to the idea of what is the limit of a sequence. Does anybody have a question or a comment about this? Okay, so let's make that clear. So this suggests our study of limits in Calc 1 should be useful, and it is. Okay. Does anybody have a comment or a question about how this kind of stuff should proceed? Okay, so here we go. Here's going to be our Calc 2 definition for the limit of a sequence. We say the sequence a sub n goes from, say, 1 to infinity, converges to L, and we write a very similar thing that we've written before. So here's what we say. We say that this sequence converges to L, and we write this if we can make A sub n arbitrarily, make that a little bigger. Close to L by choosing n, I guess, give me a second, let me write that cleaner. So if you go way back to your definition of a limit in Calc 1, you will see some word and some verbiage just like this. So if we choose our input sufficiently large, we can make the output as close to L as we want. So don't stress about this. Please don't stress about this definition right now. We have to write it down. But once we look at some examples, you will say this is very intuitive, I think at least. And then we're going to use the crap that we used back in Calc 1, the limit laws, to make this pretty straightforward. So does anybody have any question about this verbiage? Again, don't stress about it. It's not the end of the world. You should try to understand it, but what's most important is what we're going to do next. All right, so let's just look at an example real quick to help put this into more intuitive. So let's look at our friend from yesterday. Let's look at the sequence A sub n, e, this guy goes from 1 to infinity of, let's let A sub n be 1 over 2 sub n. And so we saw yesterday what this is. What is this? This is 1/2, 1/4, 1/8, 1/16, 1/32, 1/64. And that pattern continues forever and ever and ever. Now, if I said to you, what is happening, you know, at the 100th term, the 400th term, the 2000th term, the 10,000th term, well, you're going to recognize that the 10,000th term is 1 divided by 2 raised to the power 10,000. That number is, for all intents and purposes, 0. It's an extremely small number. So what are we saying here? So it looks to be the following. So we expect that the limit as n goes to infinity of 1 over 2 to the n should be 0. Does anybody not see that? Does anybody want to ask a question, or does anybody want to sort of make a point about that? Let's look at another one. 2 more examples. Let's now use a different letter. Let's use B sub n. I'm going to start this one at 0 just to be different. And let's let B sub n be given by the following formula. 2n over 3n plus 1. So what's the first term? Well, when n is 0, you get 0. When n is 1, you get 2 over 4. When n is 2, you get 4 over 7. When n is 3, you get 6 over 10. And so what you'll start to notice is that there is a pattern. The numerators are increasing by 2. The denominators are increasing by 3. Now, what would we expect? Does this thing have a limit? Well, you might not remember, but if you look at this top expression up here, the 2n over 3n plus 1, you might remember some things dating back to Calc 1. And for this guy, we expect, believe it or not, we expect the limit as n goes to infinity of 2n over 3n plus 1 to just be 2/3. Again, if you don't trust me, go evaluate the 100th term of the sequence or the 1000th term. You know, if you plug 1,000 in, you get 2,000 over 3,001. And that number is very, very close to 2/3. Plug 10,000 in. Go to a calculator, experiment, all that kind of stuff. Does anybody have a question? Now notice I'm not saying it's true, I'm saying we expect, because we haven't told you why it's true yet. Okay, does anybody have a question? Going once, going twice. All right, so, excuse me. Let's do one more example. Let's call this creature C sub n. And how are we going to define C sub n? Well, we'll define it. We'll go from 0 to infinity. This is going to be something you haven't really seen much of. Let's take -1 to the power n. So what is this sequence? Well, anytime n is even, we get 1, and anytime n is odd, we get -1. And so all this sequence does is alternate forever and ever and ever in eternity. And so what we would expect here is we would expect the limit as n goes to infinity of -1 to the power n. We expect this to not exist because it's not approaching anything. It's essentially alternating between 1 and -1 forever and ever and ever. So these are 3 important examples. I hope you study them because if the more you understand these, the better chance you have of understanding exactly where we're going to be going with this. Does anybody have a question? Going once, going twice. Okay, so here's good news. Our limit laws from Calc 1, you might not remember them, but there were plenty of limit laws. We spent some time on that way back in the beginning of Calc 1. These apply to sequences. Therefore, the three sequences above and the analysis are logically sound. So basically, all you need to do is remember how you treated limits at infinity in Calc 2, and it's the same thing. So we could write down the theorem, but it's unnecessary because we're not completely interested in sequences. As we said, we're interested in a bigger picture, but we have to start with what a sequence is. Does anybody have a question? Going once. So let's just give a moment. If someone wants to say something, please do. Otherwise, we are going to go.
In the previous slide, was that a C?
Yeah, I used the letter C.
Okay.
I'm just trying to use different letters. I can call it A sub n, B sub n, C sub n. You can use any letters you want. I just want to be comfortable with that. Just like when you have variables, they can be X or T or Y. It doesn't matter.
All right.
Okay. Does anybody else have a question? Okay, so now what we're ready to do is we're ready to study series. So here's what we're going to do. We need, as I alluded, we had this idea of an infinite sum, and we need to come up with some way of defining it so that we can actually compute it, and then it's also going to make sense and not give us ridiculous results. And now I tried to motivate that yesterday. I did a couple examples. I used decimal expansion. We need to come up with a way of defining an infinite sum, or as we define it, a series, that makes sense both from a logical standpoint and an intuitive standpoint. So, definition. Given a series, which we know, we wrote this in the following way. Let's say k equals 1 to infinity, and let's write a sub k. And now what does this mean? This means a sub 1 plus a sub 2 plus a sub 3, so on and so forth. Now, we know that this right-hand side doesn't make sense. You can't add something up forever and ever and ever, because guess what happens? You die before you ever finish. And even if you have someone take over the job, they die before they finish. It doesn't make sense to say I'm going to add forever and ever and ever. However, our intuition tells us that certain things, once we add up a few of them, we realize what's happening. We realize there's a pattern. So here's what we do. Given a series, we define a sequence. And how are we going to define a sequence? We're going to define a sequence in the following way. So we're going to call this S sub n. That's sort of the standard way to do this. So we're going to call this S sub n. N goes from 1 to infinity. This is not an integral sign, it's S sub n. Now, how are we going to define it? Well, we're going to define it recursively. We're going to define it by setting S sub 1 equal to A sub 1, S sub 2 equal to A1 plus A2, let's go to the next page. What would S sub 3 be? S sub 3 is going to be A sub 1 plus A sub 2 plus A sub 3. S sub 4 is going to be A sub 1 plus A sub 2 plus A sub 3 plus A sub 4. And of course, I think you see the pattern. What is S sub n in general? S sub n is the sum, k goes from 1 to n of A sub k. So we got lots of scary notation happening. So there's a name for this. So we call S sub n the nth partial sum. So this is a phrase that it's worthwhile remembering. So I started with a series, but what I'm going to do in order to study it properly, I'm going to rewrite it in terms of a sequence in a very creative way. Does anybody have a question? Okay, so now what this does is this gives us a very logical, sound, and intuitive definition. And so this is going to look scary, but everything's scary the first time you see it. So we are going to take this infinite thing. This infinite sum is actually going to be defined in the following way. We are going to define it as the limit as n goes to infinity of S sub n which is the limit as n goes to infinity of the partial sum. So if the limit is a number, we say the series converges. So there's that word converge. Otherwise, it diverges. So do not get overwhelmed. We're going to do an example shortly to see what's really happening. This is hard to learn, though. There's no other way around it. It is a very, very sort of conceptually difficult thing. Most of us try to learn this and we struggle. Does anybody have a question?
Yeah, can you stay on the page for a second?
I can, yeah, sure. Yeah, this is some scary stuff. But think about what's happening here, Daryl. We're saying that we know you know, look at this left-hand side. This thing is a sum that never, ever, ever ends, which means we can't add it up. That doesn't make sense. However, what we're going to do is instead of that, we're going to think about what happens when we go far out in the sum. Is there a pattern? And if there's a special pattern, that is, if there's a limit, if there's convergence of a limit, if the limit of the sequence converges, then intuitively that number is going to be what we would get if we could actually go on forever. And so it makes sense to define it this way. And it's probably not going to be as clear to you until we do an example, but that's what we're going to do now.
So if we see a pattern that looks like it's going close to one number, we would say it goes to converging.
Well, not that if it looks. I mean, look, we're going to have to see an example first because it's not right now. It's going to be hard for you and your brain to have kind of the idea what we're thinking about here. But in essence, if you look about if you consider what we did yesterday. So yesterday we said, okay, let's take this thing like 1/2 plus a 4th plus an 1/8 plus a 16th, and then a 32nd, and then a 64th. And we showed you an intuitive reason to believe that that should equal 1. But now we want to use rigor. We want to use logic to see that. So that's what we're going to do right now. So let's do that. So to illustrate, recall yesterday, we suggested that 1 is actually equal to 1/2 plus a 4th plus 1/8 plus 1/16 plus 1/32 forever and ever and ever. Right? I mean, remember, we drew that square and then we chopped that square up. I mean, if that thing on the right-hand side is going to equal anything, well, it's got to be 1 because our intuition tells us it's got to be 1. But we can't just add it up because that doesn't make sense to us. We need to think about it in a more sophisticated manner. You can't add forever. These ellipses, these 3 dots at the end say this pattern never ends. So if I say to you, add it up and show me you get 1, you're going to die. And you're not going to have gotten the 1. So we need to be much more sophisticated. Okay, so let's do this. So what we want to do is we want to deduce this in a rigorous manner. So the idea is quite simple. Oh my God, what is happening? We have ruckus in the background. You guys are getting in fights and racing cars, all kinds of things. Okay, so how do we do this in a rigorous manner? Well, we have to use series. So let's do it. So note, the series we're after is this guy. K goes from 1 to infinity of 1/2 to the power k. This is 1/2 plus 1/4 plus 1/8 plus 1/16, so on, so on, and so on. So we need to look at the partial sums. So what is our definition for this series? Well, our definition says that this guy that we just wrote down wish there was a way to erase without erasing. So what is the guy we're after? We're after this guy. But by definition, this is the limit as n goes to infinity of the partial sum. Now, we can actually write this out and analyze it. So that's what we're going to do. What is the partial sum? Well, the partial sum looks like this. It's 1/2 plus 1/4 plus 1/8. And then this thing is going to go all the way out. Let's look at the last couple terms. If the very last term is 1/2 to the n, who comes before that? The guy that comes before that is 1/2 to the power n minus 1. So we know for short what this is. This is S sub n. So this is some scary notation, and it's only going to get better if you spend time practicing and you try to learn it. You're not going to learn this in 5 minutes. You're not going to learn it watching a 40-minute video of us doing it. You're going to learn it by sacrificing your own time and energy. So again, that's ultimately up to you. You guys know my motto, though. Why not try to learn everything? Now, here's the thing. If you want to try to take the limit of that thing, it's going to be really hard as it is, because as n goes to infinity, the number of terms increase. So if we want to compute this limit, and this is what's going to be very, very important going forward. So to compute this limit, we need a quote-unquote better expression for S sub n. I mean, it's going to be really, really hard for us to take that limit the way we have it expressed. So we need to rewrite it. So here's a trick to do that. And by the way, you've seen stuff like this before. If you go back to Calc 1 when we talked about the integral, you'll remember there were certain patterns we recognized. The sum of certain things had a really nice expression. And so that's what we're going to do right now. Does anybody have a question? If anybody's even there, we never know. Okay, so here we go. We need two expressions, and we're going to write S sub n in two different ways. So let's do that. Let's rewrite S sub n in two ways. So the first way we're going to write S sub n is we are going to get creative. What's the first way to write S sub n? Well, the first way to write S sub n is to just write S sub n. And the second way to write S sub n is to actually write out what it is. What is it? It's 1/2 plus 1/4 plus 1/8. And then we go out to 1/2 to the power n minus 1 plus 1/2 to the power n. So that's the first way we're gonna write S sub n. Now what I'm gonna do is I'm gonna write it in a second way. So I'll use a different color. I'll use this blue. Now the second way I'm gonna write it is I'm gonna write S sub n, but I'm gonna multiply it by something. I'm gonna multiply 1/2 times S sub n. And that gives me 1/2 times the thing I have above. But what I can do is I can do some algebra here. I can distribute. So I can take this 1/2 and I can distribute. Etc. So if I do that, if I distribute, what I end up getting is this becomes 1/4 plus 1/8 plus 1/16 plus, now what happens at the end? This becomes 1/2 to the power n, and then the last one becomes 1/2 to the power n plus 1. Now right now you're probably thinking, why is he doing this? What's the goal? Well, the goal is to get a better expression for S sub n. And this is a trick that works in lots of different areas. You take what you're interested in and you rewrite it in a few different ways. And then maybe you can perform some algebra to get a better description. We did this with integrals a few weeks back when we integrated some of those complicated things by parts. You might remember we integrated by parts twice and we got an equation and we solved that equation. Okay, so we have two expressions. We have S sub n and we have 1/2 of S sub n. So what we can do is we can subtract. So,
how did you get like the 2n and the 2n plus 1 for the?
okay, so let's look. If I take my red pen and I come here, when I take 1/2 times 1/2, what do I get? A 1/4. If I take 1/2 times a 1/4, I get an 1/8. So I'm distributing. What happens when I take this 1/2 and multiply it by this term? What's the denominator? What's 2 times 2 to the n minus 1? So you might have to think about your properties of exponents you learned a long, long time ago. This guy right here is what happens when I take this and multiply it by 1/2. So notice, another way to think about it is look at the pattern on the very bottom line. Every one of the denominators increased by a factor of 2. The 2 becomes a 4. The 4 becomes an 8. The 8 becomes a 16. So I'm multiplying everything, and every denominator gets multiplied by 2, and that's why the powers changed. Does that make sense?
Yeah, I got it now.
Sure?
Yeah.
All right. So that's a tricky part. So that's, and that reason I write it out like this is so you can maybe see the pattern. And then the very last one, it's originally 1/2n, but when I multiply it by 1/2, I get 1/2 to the n plus 1. So it might look like I'm making a mess, but really I'm not making a mess, because what I'm going to do now is I'm going to subtract the two expressions. So this is a very, very, very useful trick. So let's do that. Okay, so now we subtract. So let me subtract. What is S sub n minus 1/2 S sub n? I want to subtract the two expressions. Well, this becomes my original expression, which is 1/2 plus 1/4 plus 1/8. So if I take my S sub n, that's what this is. Then I'm going to subtract what happens when I plug in 1/2 S sub n. Now, what was this? From the previous page, this was, well, all that was left was 1/4 plus 1/8 plus all the guys in the middle, and then it was 1/2 to the n, and then it was plus 1/2 to the n plus 1. So just to remind you of what these pieces were, up here, this expression right here, this whole sum, this is S sub n, and then underneath it, I am subtracting out 1/2 of S sub n. Now, another thing to note is that the left-hand side, which I'll use this little magenta, if I have an apple and I give my kid half of an apple, I am left with half of an apple. So look what happens in this situation. What happens is very, very nice. 1/4 and 1/4 goes away. This goes away. Everything goes away except the very first and the very last terms. So sort of like a magic trick happens, although it's not a magic trick, and what you're left with is 1/2 S sub n is equal to 1/2 minus 1/2 to the n plus 1. By doing this little trick, I'm able to show S sub n in a very concise formula. Does anybody have a question about that? By the way, this argument's in the book. It's all over the internet. It's a very common strategy to study sort of these series. So I would highly encourage that you think about it. Okay, so what we can do is we can then solve this for S sub n. Does anybody have a question before we do that? All right, so we can solve this for S sub n. So we have a new page. What is S sub n? Well, if I multiply by 2, I get 2 times what I had before. So what did I have on the previous page? I had 1/2 minus 1/2 to the n plus 1. And this is just equal to 1 minus 1/2 to the n. And now we went from a very, very ugly expression that had all these terms in it to a very beautiful expression. Right here. And now you can take a limit. Thus, what's the limit? The limit is n goes to infinity of S sub n is equal to, the limit is n goes to infinity of 1 minus 1/2 to the n which is 1, as we sort of predicted yesterday. So what we've just done is we've just logically shown what our minds told us had to be true yesterday. Is this easy? No. Is it easy to learn? No. Will you get it right in 5 minutes? No. Will you get it right in 20 minutes? Probably not. For most of us, learning this is a time commitment. And I'm not saying that to make you mad or to scare you. I want you to be real with yourself. When you can't learn it right away, it's not because you're stupid. It's not because you're not trying hard enough. It's because you're normal, and it takes a while to learn this. Does anybody have a comment or a question? We're almost out of time. So this is a very, very useful argument. Again, I keep emphasizing that, but I hope you'll take the time to learn it. So we have one thing we can conclude from this. And so we just verified, or we just deduced, that 1/2 plus 1/4 plus 1/8 plus 1/16, this sum is equal to 1. Does anybody have any questions? By the way, you could check this again for yourself. Go to a calculator and add a bunch of those up on the left-hand side. You're going to start seeing that that's exactly what's happening. What is this in shorthand? In short, we just showed that the series of 1/2 to the power k, k goes from 1 to infinity, is equal to 1. So let that scary symbol rock you to sleep tonight. All right, any questions? I don't want to go much further because I have another class. But if you have a question, I'd be happy to answer it. Or if you don't want to do it now, feel free to email me. I'd be happy to do any virtual office hours. If you want to talk about problems, obviously we can't meet in the office, but I'd be happy to do a Zoom meeting with you. We can talk about any problems, any examples you want. We can talk about life, talk about your schedule, whatever you need, just let me know. I keep clearing my throat, I'm sorry. Could be worse. I could be playing music well, you probably hear my kids upstairs acting like crazy lunatics too. You guys have any questions? No? Should I expect your silence as no? Daryl, are you alive? You usually talk. The rest of you guys, not so much. Daryl's not alive. He must be playing video games elsewhere in his house.
Obviously.
Uh-huh. All right. Does anybody have any questions? Well, I don't make fun of you, Daryl. I got a buddy. He sits down and plays Call of Duty all day.
Oh my God.
So he does. He has his work laptop, and then he plays Call of Duty all day. I said, do you do any work? He says, no. It must be nice. See, now you have to suffer through this crap so you get a job and you can get paid to play video games all day.
Paid to play video games.
Well, he doesn't. Well, I mean, that's not what they're paying him to do, but it's what he's doing. All right, listen, I got to go to the other class. I'm going to save. I'll save the whiteboards, and I am now stopping the